Okay, it looks like it made me go to a new video. Since I tried to use my calculator on my phone, I should get a real calculator, I guess. So here's what happened when I typed in the length of the board, the whole board, and the time it took to go down the whole board. So my calculator gives me this. Obviously, we have 4 sig figs in the displacement. We have 3 sig figs in the time. So I need to round that to 3 sig figs. So 515. The 6 will make the 5 go up. So we'll round there. And we'll get 0.516 for our magnitude. Unit will be meter per second. That's a velocity unit. Velocity is a vector. Displacement's a vector. So we have to have some kind of directional information. You could put a positive sign or you could say down the board, but you do need something in your lab report. Down the board. So that's the velocity over the whole length of the board. Now the lab is interested in instantaneous velocity versus average velocity. Obviously, without calculus, we can't really get an instantaneous velocity. We can get closer and closer, right? We cut the board in half. We can see that the velocity will be slower over the top half of the board than it was over the whole length of the board, and faster over the bottom half since it was already moving when it went down the board than the whole length of the board. So we can see that we can kind of narrow down average velocity into smaller and smaller sections if we actually cut the top half of the board in half again, and then we cut that in half again and in half again. We would start to approach instantaneous velocity. With calculus, you can just find instantaneous velocity at any point on a graph really easily, or any point in an equation really easily. But for us, we're just kind of cutting in half and cutting in half until we're down to a very small amount of time. We could do that, but we just cut the board in half and measured the top and the bottom half. So you kind of have to state the obvious at the end of your lab report, like, you know, the whole board was in the middle velocity wise, right? This should be a slower velocity than the bottom half of the board. It should be a faster velocity than the top half of the board. So yep, state the obvious. And then obviously you're going to compare the top and the bottom, the low board to the steeper board. So clearly the ball's going to go faster on the steeper board, and we'll learn why. Based on the angle, this angle right here, we'll learn why in a couple modules, but I won't tell you now. So yeah, this is the data you should use. Write your lab report. You can just say, for material and procedure, you can just say refer to text page, whatever the lab is on in the textbook. So you don't have to write a material list or procedure this week, but just give me objectives, conclusions, and then in the middle, the data chart, the averages, show calculations for the velocity for each trial, show your work for that. Make sure you have a direction for every vector quantity, units in your charts, and then discuss velocity, what it is, average velocity, use the lab help sheet. So next week we will try to be more organized in the lab, try to read over the lab. It's a little confusing. Come with a data chart if you think about it. So this coming week, actually, it'll be a pretty similar setup. We'll have an inclined board like this, and we'll time it for acceleration. We'll time the ball traveling down the board. That's when it's accelerating. And then we'll time it for a 1.000 meter after the board. And it won't be accelerating when it's on the flat surface. And of course, we'll talk about that a lot more. But then we will try to calculate the acceleration of the ball and we'll talk about acceleration and velocity and how they're different, how they compare to each other, what their graphs look like this week. So see you in a couple days.